Okay, welcome to the fifth lecture, fourth. This is process of the computing part 2. Okay. Topics we're going to be covering very simply. We're going to be having a look at the processor itself, what's actually happening inside the processor, and we're going to be looking at things such as clock speed, bus width, and word length. Very short little list there. First thing that made me think this might not be as long as an hour, but we wait to see. Let's have a look at the processor components first of all. We're going to just talk generally. For example, the program control unit. This takes the instructions from memory. This decodes those instructions, and then it executes these instructions. Sometimes referred to as the PCU, but the program control unit takes instructions from memory, decodes those instructions, and then executes them. The arithmetic logic unit. This, as its name suggests, performs mathematical functions, add, subtract, fixed point and floating point calculations. It also does logical, so AND, OR, XOR, as well as logical shifts. That means moving data left or right, one of the ways of using multiplication. There are a whole range of registers inside the processor. We're going to have a look at those in some detail, so I'll leave those kind of vague at the moment. The internal clock is either derived directly or indirectly from the system clock. And we're going to have a look at that as well. There are a whole series of internal buses, very similar to the data bus and the control bus and the address bus, but do not get them confused. They are not the same. Okay, these are internal to the processor. And there are a whole series of logic gates to make sure everything flows in the right direction. With things such as logic gates, obviously the logic gates inside the processor, inside each of these operations, but these are specific to flow control. And I say with the internal buses, do remember that the buses we've talked about, data, address and control, are between the processor and memory and the I/O controllers. These internal buses are inside the processor. That's an example of a processor. As we can see at the top, there is the program counter here, and these are simple logic gates sitting on there. This is the arithmetic logic unit. These are the internal buses. The program control unit we're going to be looking at in closer detail. We've got the system clock running here, and then the internal clock will run from there, and there's some general purpose registers and other components. There's the internal clock running off of there. Simple diagram. One we can have a look at closer. Okay, the registers. I said there are a whole series of these. One of these is called the stack pointer. The stack pointer points to the top of the stack. So I suppose the best thing to do is explain to you what the hell the stack is. The stack is a whole series of memory locations inside the processor, a variant number in the processor. When you run a function or a procedure, the values from that function and procedure are placed into the stack as it is running. And it's what we call last in, first out. Imagine that you're putting plates into a tray. As you put one plate down, you push it down, the next plate goes on top. So the idea is when you've got your functions, you're running your function and you declare a variable inside that function, then the value for that variable is actually stored inside the stack. And the next variable is put on top of that value. That means that if I wish to get to the lower value, I actually have to take the top plates or the top variables off. The stack pointer is given the address for the last value entered into the stack. So the stack pointer is always pointing to the last thing put into the stack. Therefore, it's always pointing to the top of the stack. This is a very fast way of storing your local variables. If your function ends, the other thing it stores right at the bottom of the stack, the very first thing it puts in is the return address, where it's got to go back to. So when your function or your procedure comes to the end, the last thing it takes out is the address of where it goes to, and it loses all the values. That's why local variables stay within that function or procedure, and you can't use them outside, because the stack is cleared. The stack pointer, therefore, is used to point to the upper value in the stack, and therefore is considered to be pointing to the top of the stack. Program counter. Program counter stores the address of the next instruction to be executed by the processor. So it holds an address, and it holds the address for the next instruction, not the current instruction, but the next instruction. The status register. There's a whole series of status flags in the system. There are basically, when you set a value, they're called flags because the idea is mentally imagine that they pop up. They don't. They're set as 0 initially, and if something happens, they're set to 1. One such flag is what we call an add with carry. If I add a number up and it exceeds the number of bits I've got available, then the carry flag will come up to tell me that the number is bigger than I've actually got as such. There are a number of flags inside of the system. He says hunting for all the different variety of types. I haven't written any down. That's really cool for myself, isn't it? I haven't given, but there are a whole load of flags. The add with carry is certainly one of them, and there are others to tell you what's happening inside the processor, or to tell the processor what's happening. The accumulator. This is actually the workspace of the processor. This is where all the values and all the executions are undertaken in the accumulator. Sorry, the latest value undertaken by the process is stored. So it's an immediate piece of memory that the ALU talks directly to and stores data within. The current instruction register, sometimes known as CIRs or IR, just the instruction register. It's worth remembering that it's called the current instruction register, so you don't forget what it actually is holding, which it holds the current instruction. And it holds the current instruction from the moment it's been received at the end of the fetch sequence, through decoding, through execution. So for the whole time that the command is being executed, the CIR is holding the latest instruction. I think its name suggests what it deals with. This deals with the address. And this is the address of the current instruction. It holds, as I say, the address, so it points to, at the end of the day, it points to the location which holds the instruction that we wish to execute. The alternative to that is MBR. You will also see this as MDR, or data register. Sometimes it's worth remembering that. I must admit I grew up with MBR, so I'm quite happy with that one. But data is what its business is. This is where data is either stored from memory or used before sending data to memory by the processor. It stores the instructions and the data values. Okay, system clock. Inside your computer is a small slither of quartz. There's quartz. That's a quartz crystal, and that's what we carve them down to. Now, the one thing we know about quartz is that when you slice it and you apply a voltage to it, it vibrates, or it actually oscillates, which means it changes its shape. And we know the frequency at which it does that. It varies depending upon the voltage being applied. Since we know its value, we know how fast that is per second. We can use that as a base of timing. And so we've used quartz to do timing of our computers. We then use circuitry to multiply that up or divide that down or however else. We measure those clock speeds in hertz, H-E-R-T-Z. This is a kind of animated version of hertz. As you notice, when it's 1, it actually is one complete cycle from beginning to end, starting the journey and ending where it started up. As we increase the frequency, we increase the hertz. As we increase the hertz, we can continue more cycles per second. Computer processors generally can run anything from 1 million to 1 billion cycles per second. I thought I'd do a quick calculation. That means if you've got a 6.3 gigahertz processor, your processor is undertaking 100 times more processes per second than there are human beings in the United Kingdom. Every single cycle of that system, for each cycle, the computer will perform an instruction or an execution or something along those lines. The frequency of the clock is known as the clock speed, and you have 2 clock speeds potentially. Ideally, your clock speed of your processor should match your system clock. So as I said before, your processor is either directly or indirectly connected. Ideally, they should be the same speed. But due to innovations in processors, due to limitations in speed of memory, you actually will find that the system clock is slower. And we use multiplication systems inside the processor to increase the clock speed. The system clock may well be the processor's clock, the clock speed, will be a multiple of the system clock, and the system clock you'll often see referred to as FSB, or front side bus. That just tells you the speed of the motherboard, from the components to the processor. Your processor will work at a faster rate quite frequently nowadays, but ideally it would be nice to have them matched so everything's communicating at the same time. An increase in processor speed, as you can see, when we get to 1 again, if I can complete 1 execution per cycle, then if I increase the amount of frequency, if I can increase the hertz, then I can perform many more cycles and therefore many more executions per second. However, be very aware there are a hell of a lot of other things that interfere with the way the processor works. Focusing purely on clock speed would be a fallacy. It does not necessarily mean your computer is running faster or better than someone else's. It's one measure. Okay, word length. This is kind of strange because you'll find, particularly in your textbook, that they connect this with something else we're going to look at in a second. And there is a good correlation between word length and what we're going to look at, which is bus width. But they are not the same. The word length is the maximum number of bits your processor can accept or process at any one time. So if you have a 64-bit processor, it means it can have 64 bits it can execute at any one cycle of the clock. So the word length is down to the processor and what it can handle and process, what its internal registers can. That means that it's dedicated for an instruction or a value or a calculation or whatever else. Von Neumann architecture, as you're aware, can have data and instructions all within the one system. So that means that if you've got a 64-bit von Neumann processor, then you're going to have a word length of 64 bits. But a Harvard system, because data and instruction are separate, you can actually have differing word lengths. This is the one they get confused with. Bus width. The bus width is how many physical wires run across your system from the processor to the memory or back. So parallel lines that run data or address. Because quite often you'll get a computer which is bus width is the same as its word length, then you'll get confused between the two. But there is no reason why your bus width has to be the same. In fact, you can run a 64-bit processor on a 32-bit bus line. What does that mean? Well, it means that for every execution the processor could undertake, your bus width has to carry the data twice. So if it's got 64 bits in its memory that needs to go to the processor, it will send 32 bits and then send another 32 bits. So they normally will be similar nowadays, but there's no reason why they have to be the same. They are always a multiple of one or the other. Okay, let's have a look at making changes. What if we change some of these characteristics? So what we're going to have a look at is things such as, what if we change the clock speed? What impact does that have upon our computer? What about how many cores we have inside our computer? Does that make any real difference to our computer? What about changing the word length or the bus width? Those are 4 areas that you actually have to be concerned with and understand. Let's look at clock speed first. Simple graph looking at speeds and processors over time, and we can see that the speeds have been increasing quite substantially. Given if everything is equal and I have 2 processors, a 1 gigahertz processor and a 2 gigahertz processor, then the 2 gigahertz processor should execute any command twice as fast. It is that simple a calculation. It is never that simple, but it's a good way of recognizing that actually change the clock speed and it does improve the system. There are certain things that we've had over time that limits how fast we can make our computers, and the prime one is heat. There is a concept, this is looking at something called Moore's law. Moore's law, sorry, go back, it's gone, haha, good. Basically, Moore's law stated that transistor compaction, the ability to compact transistors into small space, will double every 2 years. Originally he said 1 year, 1965. In 1975 he changed that to 2 years. And actually we have found this, we have been able to compact more transistors into a processor, and that's the general trend from 1971 to 2011. And though we have had deviations and what looked like a breakaway, a collapsing, this was happening because of heat. It was more and more difficult for us to pack more transistors in because more transistors require more electricity. More electricity means more consumption, which means more heat, and you've got to get that heat away from the processor as quickly as possible. There is a certain point at which you can't extract the heat fast enough. Now obviously we're not talking about transistor count, we're talking about clock speed, but clock speed's the same. If I don't increase the number of processors, but I increase the speed of the system, then it's also equally demanding more power. And if it's demanding more power, we have got to lose that heat as quickly as possible. I saw a quote recently that said, if we keep going with the way we are as regards heat, in 20 years' time, our processors will generate more heat than the surface of the sun. I haven't been able to find any proof on that. But I have seen people cook eggs on processors. They get that hot. Multi-core processors. There's a shot of how they're separated up. So you've got your memory controllers, and these are the 4 cores, common queue, and a shared cache. This is, those for you from last week, will remember we looked at different types of RAM. This is the incredibly fast RAM that sits here that helps to make everything much faster. One of the ways that we can reduce the problem about speed and the problem with transistors is to pack more processors onto a single processor. So a multi-core processor is exactly what its name suggests. It means that this one has actually got 4 processors running at the same time. we term the processor's core, since the whole thing is called a processor. Multi-core processors allows the system to execute code on each core at the same time. But don't think that's going to mean that your programs are going to run faster. These programs still need to execute in series. It still needs to take one command and then the next command and then the next command. Your single program is unlikely to run any faster. It won't run any faster if you've got 4 cores or 1 core. If you're running Microsoft Word will run in one of those cores and won't use the other ones. Where multi-core comes in useful is if you have 3 or 4 programs running. They're designed for multitasking. So if you want to know why you have a multi-core processor, you have a multi-core processor because you want to run multitasking. There is something called multi-threading. And what this does is it uses what we call latency of the processor. The idea is that your processor executes a command and then it asks for something to come from main memory. Now that's going to take 10 or 15 cycles of the clock for the data to get from here to the RAM and get back. That's latency. That's time when your processor is sitting there going, oh, I'm a bit bored. So what we do instead is they use multi-threading to say, well, if the processor's not busy, then get some other commands in. Let's get some other things processed. Multi-threading is a really clever idea. It's got the misconception that it means that your program is being parallel processed. That's not true at all. Your processor is still running commands one after the other, but it's doing so now incredibly quickly. If I run a multi-thread across several processors, or several cores, then it's parallel processing. But also be aware that you can't simply build a program and assume it's going to run as a multi-thread. You actually have to write your programs as multi-thread programs. That means breaking your program down into small executable chunks all by itself. So multi-threading is very useful. Multiprocessing is really useful, but it is down to the programming, it's down to how it's going to be executed, it's down to how busy your computer is overall. Okay, so what if we increase the word length? Let's have a look at a simple, this is a 24-bit instruction. That is what we call the instruction. This is the opcode. This is the bit that tells the computer what to do. And this part here is a value, which is just overlapped. If I have a 16-bit word length, then I can only execute the instruction and half of this number. I then have to wait for the cycle of the clock to allow myself to send the second part before I can complete the operation. So what I would then need to do is, if I could increase the word length by getting a new processor that can handle other word lengths, I can then execute the whole 24 bits. And if I can execute it as one single cycle, I've just made my processor a hell of a lot faster. What about the bus width? Well, if I increase the bus width for the address bus, so I add another line. Now remember, these are wires and they are running in parallel across the system. So if I run another wire alongside, and you can't just simply go down to Maplin's and buy a piece of wire and solder onto your motherboard and go yippee. It's actually got to be manufactured into there. But the simple fact is, if I increase the number of lines from the address bus, I increase the amount of memory I can address. If you think about one wire, I can only address then 2 separate bits, 0 or 1, which means that I can only have 2 memory addresses. But if I have 2 wires, I can now address 00, 01, 10, 11. I've just doubled the amount of memory I can have. And that's true for every wire you add. It's useful to know that if I increase the address bus by 1 wire, I double the amount of memory I can now address. If I increase the data bus, as long as I don't try to exceed the word length, but if I increase the data bus, then obviously I can carry more data, and if I can carry more data at any one time, my processor can execute that data, and therefore I get faster processing. So we've talked about the internal parts of the processor, we've looked at the bus width, we've looked at the word length, we looked at all the separate areas, the registers and everything else. What I'd like to do now is have a look at actually what is happening really right inside that computer. What is happening inside that program control unit? Let's have a look at a piece of code. This is simply mnemonic. This is the binary conversion. That is what the machine actually executes. And that's the hexadecimal. Those of you that have been coming to every lecture, this should begin to become familiar. What is this doing? Well, this is loading a value 10 into the accumulator. Remember, the accumulator is the area of the processor which the ALU works with. So when you say load a number in, load the number 10, it means load the accumulator. This is my quick workspace. It then says store 25, which means there's no hash, so it means store whatever's in the accumulator in memory location 25. Now load the accumulator with 24. Then add whatever's in the accumulator to memory location 25. Store 25. So store the value at 25. This is doing exactly the same. This is doing exactly the same. It's simply saying take 10, add 24 to it. So again, when we looked at programming before and I said, look how simple our modern day languages are, that's what I would type, but that's what I would have entered previously, and that's just horrible. Those are the opcode. Those are the instruction sets, or the instructions that are executed by the processor. Those are the operand. These are values, either memory addresses or values that are being passed. Each instruction set comprises of an instruction and an operand of some form or other. And just for clarification, that's what an instruction set is. It's a set of instructions that the processor knows how to execute. Just have another look at that program. So we've got there the 6-bit machine code instructions, 16-bit, sorry, the hex code, the mnemonic, and simply an explanation. So place 10 in the accumulator. Place a copy of what's in the accumulator in 25. Notice the accumulator doesn't get deleted. It's still got 10 in it at this stage. Then it says load 24. I don't know why the hell I've got 6 in there. I didn't type that one correctly. I was getting tired. It means load 24 into the accumulator. Add whatever's in the accumulator to memory location 25. Sorry, to add memory location 25 to what's in the accumulator, and then store the accumulator in memory 25 again. We end up with 34. Okay, here's some components that you need to know when we're looking at what we call the fetch execute cycle. The program counter, the accumulator, the current instruction register. We've already talked about all of these earlier. Please note, and this is really important, if you see square brackets, it does not mean I'm talking about the program counter or the accumulator. I'm talking about the contents of those areas, what they are currently storing. Okay. What I've now done there is I've now given you the mnemonic but with the memory address. Now I've just simply chosen an area of memory. It doesn't have to be those values, but I've selected them. So in memory location 200 will be this data instruction. In memory location 201 will be this memory location, or this memory instruction, and so on. It actually looks like that in the binary. This is the address part, and this is the data part. When the address bus is working, it will work with this, and when the data bus is being used, it's this that will be traveling down it. The commands are relatively simple. The first part of the fetch execute cycle is that the contents of the program counter are transferred to the memory address register. Remember that the program counter holds the address for the next instruction, the address for the next instruction. So that is at this point, at the beginning of the fetch execute cycle, that is being transferred to the MAR. As soon as the MAR gets it, that opens up. It uses the address bus to point to that memory location and basically says to the memory, in a moment you're going to hand us what you've got at that memory location. These two happen exactly at the same time. What I've got here is the memory at the location being addressed by the MAR is passed to the memory buffer register. So the PC, first of all, transfers the content to the MAR. That opens up the address so that in the next cycle of the clock, the data in there is transferred to the MBR, not the address, the data. At the same time, the program counter, its content will increase by 1, so it's now pointing to the next instruction. So it's only at this point here, for one cycle of the clock, the program counter and the MAR both have the same address. Finally, the contents of the memory buffer register are passed to the current instruction register, and that ends the fetch part of the fetch execute cycle. That is the standard notation to say that is how it works. Let's look at the first part. So the PC, when I switch my computer on, the PC will be set to the default first address. And in this case, it's going to be 11001000. That's the first instruction. That is when I switch my computer on. The processor then starts the fetch execute cycle. So it goes into the first part of the fetch, which is this part here. It takes the contents of the PC and passes that to the MAR. So the MAR and the PC now have the same value. The next cycle of the clock takes us to this line here. That means that the contents of that memory, this data here, is then passed to the MBR. At exactly the same time, the PC has 1 added to it. It was originally 000, it's now 001. It's had 1 added to it. So now what we've got is the PC looking at the next instruction, the MAR holding the current instruction address, and the MBR is holding the current instruction itself. The final part is to transfer the contents of the MBR into the current instruction register. And that is the fetch sequence completed. From the fetch sequence, we then go to the execute. Now the execute, as it says here, is that the current instruction register automatically separates the instruction into opcode and operand. As soon as it's received the data, at the next cycle, it passes the opcode to the instruction decoder. The instruction decoder then decodes the instruction, executes the instruction, and utilizing the ALU and the accumulator, executes that instruction and then goes back around and allows the fetch sequence to start again. So the execute cycle doesn't have a nice little pretty chart because it's just a simple case of the CIR separates it into opcode and operand, passes the opcode to the instruction decoder, and the instruction decoder then looks at that instruction and says, right, what have I got to do here? Oh, that's what I've got to do. I need the ALU, I need the accumulator, let's get it done, then moves on. That part is going to take several cycles of the clock. That's what takes time, as the processor works out which part it needs to work with and everything else. Let's have a closer look. That's my code. What I've got here is this is my executable area. This is my program memory area. My computer will separate my program, my memory, into the operating system and everything else. And this happens to be the area that my computer has allocated for executing programs, and it would continually run down. This is the RAM. You may notice that these are the instructions I gave you earlier. It's exactly the same piece of code. This is load the accumulator with 10. Store the value in memory location 25. It's the same instruction set. This one here is actually simply there because this is where my program would store values if I need to. So if I need to store a value to RAM, it's this area here that is allocated by the computer for that purpose. The program counter, when I switch my computer on, is automatically pointing to the first address for the executable area. That's before that, just as I switched it on. Now we start the fetch execute cycle, the fetch part of it. The program counter gives the address to the MAR. Once the MAR has it, immediately it opens up that address location. So it points to that. This isn't pointing to that memory location, it should have been up there, but it's pointing to RAM and it's saying to RAM, I want that memory location to be opened up, please. The data is then transferred. This data here is transferred down the data bus to the MBR. So this data enters the MBR. At exactly the same time, the PC is updated by 1 and therefore points to the next location. The MAR still points to the current instruction, and the MBR now holds the current instruction itself. The processor then transfers the contents of the MBR to the CIR, immediately separating into opcode and operand. This one, remember, is load the accumulator with 10. The next cycle of the processor, of the clock, the CIR will pass the instruction to the decoder. The decoder then will decode what it needs to do, load the accumulator, and it will tell the ALU, I need the accumulator and I want you to store 10 in there. And that might take 5 or 6 cycles of the clock to perform. Then what happens is the PC then updates the MAR with the next address. Because that's the fetch execute cycle finished, it goes right back to the beginning. That means that it opens up this memory location, which means that the data at this one is moved into the MBR. At exactly the same time, the PC is updated to the next address. This one, remember, is store whatever's in the accumulator in memory location 25. The MBR is transferred to the CIR and we have finished the fetch part of the sequence. The CIR has automatically separated that data into opcode and operand. It then transfers the opcode to the instruction decoder. The instruction decoder decodes that instruction, executes it, and takes that address with that value and redirects that to the MBR. The MBR now takes the new value, which happens to be the same value there, And it is the MBR that will transfer that to memory location 25. That's two complete cycles of the fetch execute system. And obviously, it would all go again. We've looked at the stack pointer and that it points to the top of the stack. I've explained what the stack is, that it holds the values of the functions and formulae of your variables as you're going through, plus addresses. Program counter we've seen holds the next instruction. We've seen how that works in the fetch execute cycle. Status registers, as I say, I've mentioned predominantly the carry, but there are a number of other registers in there. They're either general purpose or they are ones that have a specific role within the processor. The accumulator we had a look at. We've seen how these components perform the fetch execute cycle. We had a look at the clock speed, at bus width, at core count, and at the other one, word length, and how, if we change those, how they would affect the performance of our computer. And then we had a look through the fetch execute cycle. I hope that was useful. Okay. Thank you very much. Have a nice time.